Assalamualaikum and very good morning. So for today's lecture, we're going to continue uh, with our lecture 9. So from part 1 of lecture 9 before, we did learn about the parameters of the photodiode. Yeah, the last part of lecture 9 part 1. We have learned about the parameters which include the absorption coefficient and also the long wavelength cutoff, lambda c. So for the third parameters, we're going to learn about the quantum efficiency, quantum efficiency of eta, in which the quantum efficiency is defined to be a ratio between the primary pairs of the carrier created by the incident photons divided by the number of photons incident on the diode material. Okay, so we have learned from the early part of lecture 9 that for photodiode, the light or the photons will be incident on diode material, and this photon or light will then excite, or produce a carriers which include the electrons and the holes. Okay, so the electron and hole pairs basically is produced by the incident photons on diode material. So to calculate the quantum efficiency, of this photodiode, this is the formulation that shall be used, in which we want to calculate, and we need to know what is the amount of carrier pairs created, okay, by the incident photons divided by the numbers of photons incident on diode material. Okay, so based on this equation, we can say that the major factor that determines the quantum efficiency will be the absorption coefficients of the semiconductor used. Okay, because we have learned before that absorption coefficient is the ability of the material or the semiconductor to absorb the photon. Okay, so if we have a higher amount of photon absorptions, so the quantum efficiency value should be higher. Yeah, so that should be the major factors that that determines the value of quantum efficiency. Okay, so normally this value of quantum efficiency should be less than unity or less than 100%, because it is known that not all incident photons will be absorbed to create the electron hole pairs. Yeah, so we have the incident photons, but not all of these incident photons will create the carrier pairs. Okay, so that is why we cannot get the 100% value of quantum efficiency. Yeah. Okay, so this quantum efficiency normally is quoted in terms of percentage. For instance, 75% of quantum efficiency means we have 75 pairs of electron and holes created by 100% or 100 numbers of photons incidents. Okay, so that's what I meant by 75% of quantum efficiency. Okay, and the interesting things is that the quantum efficiency is also is said to be a function of wavelength. Yeah, because seems like absorption coefficient, because we know that if the absorption coefficient is said to be depending on the wavelength, and we know that the quantum efficiency is highly depending on the absorption coefficient. So by right, this quantum efficiency must also be a function of wavelength. Yeah, right. So this is about the quantum efficiency parameters. Okay, the next parameters to be learned is the responsivity, the R. So responsivity is defined to be a ratio of current, right? Ratio of current output to the light input power. Okay, so the formulation for responsivity is IP over P naught, where IP is the output photocurrent, which is the current produced when the carrier pairs, electron and hole, start to flow in the PN junction or in the diode structure. Yeah, so this photocurrent is produced from the movement, from the flowing of these carrier pairs. Okay, and the P naught is the incident optical power, which is the light incidence on the photodiode. Okay, so that is why we have the responsivity is given by this equation. Okay, and the responsivity will be depending on the wavelength, right? And this will be the formulation that can be used to calculate the responsivity of the photodiode, where the eta here is your quantum efficiency value, E is your charge amount, lambda is the wavelength operation, H is the Planck constant, and c is the speed of light. So this is the equation that can be used to calculate the responsivity of the photodiode material. Okay, so for this particular slide, it shows that the responsivity is depending on the wavelength. Yeah. So the first diagram here, the first figure here is for the case of silicon photodiode. Yeah, silicon photodiode, where we have two cases. The first one is for the ideal case of photodiode, where the eta is equals to 100%, or the quantum efficiency is 100%. And second one, this diagram here is for typical photodiode, which is the practical, yeah, the practical photodiode, the real case of photodiode. Okay, you can see that from this diagram for the ideal photodiode, yeah, for the equations of R equals to eta E lambda over Hc, which we have seen before. We can see that for this responsivity, the N, E, H, and C is a constant when we consider that eta, or the quantum efficiency, is 100%. Okay, so R is said to be proportional to the lambda, yeah, where the constant is equals to eta multiplied by E divided by H multiplied by C. So that's why we have a straight line, yeah, for the case of ideal photodiode. Okay, but in a real case scenario, where eta is not constant, yeah, it's not constant, okay, and eta is known to be depending on the wavelength, so that's why we have a responsivity graph against wavelength which looks like this. Okay, and it's depending on this equation, and it's depending on the lambda, yeah, because we know that the quantum efficiency is depending on the lambda. So for every lambda value here, the eta, or the quantum efficiency, will be depending on it. Yeah. Okay, so note that the quantum efficiency, I mean the responsivity, will increase according to the wavelength as given by the equation, but up to a certain position, up to a certain point, the responsivity will drop rapidly. Okay, so this position, or this wavelength value, is what we call as a long wavelength cutoff, yeah, where above this wavelength, the photodiode cannot function properly, yeah, and as such, it can be said that the responsivity will drop, yeah. All right, and the second graph here shows the responsivity versus the wavelength for other type of semiconductor material, okay, which include the indium gallium arsenide and also germanium. Okay, this is a silicon which is same as above, right? So from this diagram, it can be seen that the silicon and also the indium gallium arsenide material, both of them can achieve up to 90% of eta, or up to 90% of quantum efficiency. Yeah. So this is a line. Yeah, a line which shows that a graph of responsivity which intersect with this line will achieve the 90% of quantum efficiency. So from this particular graph, it shows that it is possible for the indium gallium arsenide and silicon-based photodiode to achieve a very high percentage of 90% value of quantum efficiency at certain wavelength only. For instance, for silicon, it can be achieved at this particular wavelength, which is around 0.8, whereas for indium gallium arsenide, 90% of quantum efficiencies can be achieved at this particular wavelength, which is about 1.2 micrometer of wavelength, yeah? Okay, and from this graph, we can also see that a very high responsivity can be achieved at 1.55 micrometer, yeah? 1.55 micrometer, which is a commercial wavelength used in optical communication. And this can be achieved for a photodiode fabricated by indium gallium arsenide. Yeah, so this is about the 1.55 micrometer. So it can be achieved for the case of photodiode fabricated by indium gallium arsenide material. Yeah, yeah. And again, as I mentioned before, at certain wavelength, the responsivity will drop rapidly. Yeah, and this happens at the wavelength value, which is known to be a long wavelength cutoff. Yeah, for each photodiode material. So for, let's say, for example, for germanium, it happens about around this value, which is about 1.4 micrometer. For indium gallium arsenide, it happens somewhere around here, which is a bit, yeah, it's about 1.6 micrometer wavelength. Okay, and for the silicon, Yeah, it's about this value, which is about 0.9 micrometer wavelength. Yeah, so that should be the value of long wavelength cut off for respective material of photodiode. Yeah. Okay. So let's have a look at this example where we are given in this example a 3 times 10 power of 11 numbers of photons with a wavelength of 0.85 micrometer are incident on a photodiode. Okay, so we are having a photon incident, numbers of 3 times 10 power of 11 photons numbers. A wavelength of photons is or light is 0.85 micrometer, and incident on the photodiode an average of 1.2 times 10 power of 11 electrons are collected at the terminals of the device. Okay, so when we have 3 times 10 power 11 photons, then we have 1.2 times 10 power 11 electrons produced. Yeah. So the question is determine the quantum efficiency and responsivity of the photodiode at 0.85 micrometer. Okay. So for the case of quantum efficiency, we have learned before that the quantum efficiency or having this symbol eta is equals to numbers of carrier pairs. Okay, number of carrier pairs divided by the number of photon incidents. Okay, number of photons. Okay, and we know that from this information of the questions, we have about 1.2 times 10 power of 11 numbers of carrier pairs or electrons. Yeah, and number of photon incidents is 3 times 10 power of 11 photons. So based on this, we can calculate that the eta, the quantum efficiency will be equal to 0.4, or in percentage, we can have it as a 40% of quantum efficiency. Yeah. Right. So the second one is about responsivity. So responsivity R will be based on the equations of eta or quantum efficiency multiply with the charge amount multiply with the lambda wavelength of operation divided by time constant and also the speed of light. Okay, so this will be the equation that shall be used to calculate the photodiode responsivity. So we know that from the first question just now, the quantum efficiency is 40%, or simply we write it as 0.4. The charge amount is 1.6 times 10 power of negative 19 coulomb. Okay, the lambda is 0.85 micrometer divided by the h, which is equals to 6.62 times 10 power of negative 34 joule second. Okay, whereas for the C will be 3 times 10 power of 8 meter per second. Okay, so from this, we can then calculate that the R for this particular photodiode will be equals to 0.274 ampere per watt. Yeah, so that will be your responsivity for the given examples here. All right. Okay, so next parameters is response time. Okay, so response time will be covered in detail in chapter 6, yeah. But for the time being, we just state here that response time is a time needed for the photodiode to respond to the optical input or the light and produce the external current. So the response time will be depending on these parameters, yeah, the capacitance, the load resistance and design of photodiode. So normally we are measuring the response time with response to square input impulse, and it's measured between 10% and 90% of the amplitude. Yeah. So we base on this diagram down here. So response time is measured between 10% and 90% of the amplitude. Okay, so that should be the response time or the rise time of your photodiode. So these topics of response time will be learned later in chapter 6, yeah, but we know for up to now that one of the important parameters in a photodiode is a response time. Yeah, right. Okay, so that will be the parameters of photodiode that need to be understood. Yeah, need to be understood. Right. So now we're going to proceed with the principle of operation for the photodiode. Right. So as what I've mentioned before in the first part of lecture 9, that photodiode is basically having similar structure with the LED and also the laser diode LED that we have learned in chapter 7, in which is simply it is a PN junction. It's just a PN junction, okay, PN junction, which the junction can be exposed to the external light. Okay, so this is one of the special characteristics, yeah, of the photodiode, whereas one of the junction can be exposed or need to be exposed to the external light so that the photodiode can function properly. Okay, but as opposed to this laser diode and LED that we have learned previously, the photodiode is said to be reverse bias. Yeah, diode is said to be reverse bias. Yeah, and when we have a reverse bias condition, the electric field will be developed across the PN junction. Yeah, and it will sweep the carriers, the majority of the carriers, hole and electrons to the respective majority sites of P and N type. Yeah, and this will further create the depletion region. Okay, so we consider that this is your PN junction. Yeah, PN junction. So there's a P material, there should be the N material. So when we have a reverse bias condition, so the negative terminal will be connected to your P junction or P material, whereas the positive terminal will be connected to this N material. Yeah. So when we have this reverse bias condition, yeah, the majority of the carriers, for instance, in the N will be the electrons. Yes, with the majority carriers in the N material. Yeah, whereas for the P material, the majority of the carriers is hole. Yeah, will be the hole. Yeah, the majority of the carriers. Okay, so when we have this reverse bias condition, yeah, these electrons and these particular holes will be attracted. Yeah, will be attracted to its opposite polarity. Yeah, opposite terminal. Okay, and as such, when we have this condition where the electrons, the carriers of electron and holes, which are said to be attracted to this terminal, yeah, we are going to have a depletion region. Depletion region which is produced due to a formation of a positive donor atoms, yeah, and also a negative acceptor atoms. Okay, so we have a formation of depletion region as a result of the migration of the majority carriers, which is attracted to this terminal, yeah, to the terminal. So we have, this is your depletion region, yeah, that should be the depletion region of your PN junction as a result of this reverse bias condition. And it can be said that the depletion region will be wider, yeah, will be wider due to this particular case of a majority carriers migration, yeah. But at certain point, yeah, at certain point, there should be a, this barrier will be a constant, yeah, will be having a constant width, yeah, will be having a constant width. And as such, we can see that at this particular case, there exists a barrier potential, yeah, yeah, barrier potential due to this existence of a positive and negative charges on this depletion region. Okay, right. So for this particular case, we can see that at this particular P material, there is a minority carriers of electron. Yeah, this is minority carriers of electron, and also at this particular N or N material, there is also a minority carriers of the hole. Okay, so this minority of carriers, electrons and also the hole, it can move, yeah, across this depletion region or the barrier potential because of the attraction of the terminal. And the same things applied for this minority carriers of holes in the N material. It will move to this P material as a result of attraction by the terminal. So this case of electron flows and also hole migration, when there is no incident photons or there is no incident light in this particular PN junction, will result in the flows of current, and this current is what we call as a dark current. Yeah, dark current, or also we call this as a reverse leakage current in the diode. Yeah, this is a result of the migration, the flowing of carriers, or I can say the minority carriers, which are the electrons in the P material and holes in the N material, without the incidence, without the photon incidence on the PN junction of the diode. Yeah. Okay. So that should be the case of the PD of the PN junction of the photodiode. Okay. A photon incidence, which need to be having energy bigger than or equals to the background energy of the PD material. Yeah, so this photon incidence will excite the electrons from valence band into the conduction band. So this is a case whereby a carriers is said to form. Yeah, is said to form where we have a formation. Yeah, formation of electrons and holes, yeah, as a result of incidence of these photons. Yeah, so when we have the photons, electron will move from valence band to conduction band, and it will leave the empty hole. So now we have a formation of electron and hole pairs. Okay, so this is a result of excitation. Yeah, excitation of these of photons to this particular electron and hole pairs, and what we call a photogeneration process of the carrier pairs. Yeah. Okay. Uh, Next, we can see that the carrier pairs which are produced or generated by the previous photogeneration process in your photodiode or in your depletion region. Okay, so we know that for the previous case, yeah, for the previous condition of this photogeneration process, this happens in your depletion region. Okay, it happens at the depletion region. When we have a light incidence on the depletion region, so there should be a formation of carrier pairs, yeah, and it happens in the depletion region. So these carrier pairs will be then separated and drifted. Yeah, it will be drifted under the external electric field application. So we have, this is a depletion region just now. Okay, this is a depletion region just now. So we have, when we have the incident photons, yeah, when we have the incident photons applied to this particular depletion region, so we're going to have a formations of electron and holes as given by this. So electron will move, yeah, we move to this positive terminal, hole will move to this negative terminal, and as such, we're going to have a flow of current in this circuit of your photodiode. Okay, so this movement, yeah, of the carrier pairs, as I mentioned just now, will then produce the current in the external circuit, yeah, and as such, we can say that the photodiode is now to be fully operated. Yeah. Okay. But one thing to be considered is that when we have, yeah, we prefer to have a very wide, yeah, a thick depletion region, because we know that the light incidence will happen at this depletion region. Yeah, will happen at this depletion region, and the carrier pairs will be generated in this depletion region. So as such, we need to have a thick depletion region so that more carrier pairs can be generated. But things to be remembered here is that if we have a thick depletion region, yeah, it will take a longer drift time for the carriers. Means that if you have a thick depletion region, it will take longer time for the electron and the holes to move to the opposite terminal. Yeah. So as such, this longer drift time will incur a reduction in the speed or response of the photodiode. So this is one of the things that need to be remembered. Yeah. Yeah. So when we need to have a thick depletion region, so that, as I just mentioned just now, thick depletion region is very good because we want to have more carrier pairs generated. Yeah, because light will be incident on this depletion region. Yeah, so when we have more carrier pairs generated, so more current will be produced in your circuit. But when we have thick depletion region, the effect will be more time will be taken for the drift of the carrier pairs to take place. Yeah, and as such, when we have longer drift time, the speed of operation or the response of your photodiode will be slower. Yeah, will be slower. The speed will be slower. So that should be the drawbacks. Yeah, the drawbacks of having thicker depletion region. Okay. Right. So I think I'm going to stop now. Okay, going to stop now. So hopefully by now you have understand the few parameters of the photodiode. Yeah, which include the quantum efficiency. Okay, I also covered the topics of responsivity. Yeah, and also the response time. Okay, and also we did learn about the principles of operation for the photodiode. Yeah, starting from this understanding on the p-n junction, the reverse bias of the photodiode, the production or the formation of this depletion region. Yeah, so by right we're going to have a thicker depletion region for the case of reverse bias condition of your photodiode. Okay, and then we know that the carrier pairs will be generated in your depletion region because we know that the light will be incident on this depletion region, and such at this depletion region the carrier pairs will be generated. Okay, and the carrier pairs which are said to be generated will move, yeah, to this opposite terminal. Yeah, so when we have a moving or flowing of these carrier pairs, the current will be produced in the external circuit, and then the photodiode is said to be operated. Okay, but the drawbacks of having thicker depletion region is that more time will be taken for the carrier pairs to drift. Yeah, and as such the speed operation or the response of this photodiode will be reduced. Okay, so these are the things that we need to understand in the case of photodiode operation. So I'm going to stop here. So we're going to meet again in part 3 of lecture 9. So with that, thank you very much, and we're going to meet you again soon. Yeah, thank you.